Welcome back to ECE 441A, 541A. You have this lecture and the next lecture prior to exam number 1. Exam number 1 is scheduled for Friday. Homework 2 is due on Wednesday, and I will try to post those solutions on Thursday. Obviously, you can tell that you haven't had your first set graded. It's taken us a while to get graders positioned. But hopefully you can check the solutions and you maybe retain a copy of yours so that you can grade your own relative to your understanding of that material. Exam number 1, there are practice exams on D2L for you to look at, examine. That's what I would suggest you do, is try to take 1 or 2 of those on your own without too much looking at anything, and see where you still need to concentrate your efforts in terms of studying for the exam. Show of hands, how many people have completed lab number 1? Okay, if you haven't completed lab number 1, you're not completely lost, but you'll definitely want to know the material for lab number 1 prior to exam number 1. So even if you haven't executed the lab, make sure that you understand how to use the information or the material so that you can work the problems on system identification that will be on exam number 1. You should all be teamed up and ready to go. If you haven't yet, you can sign up for a 1-hour time slot in the stock room, which is ECE 351, and hopefully you can communicate with all of your team members to make that happen.
On the practice exams, you mentioned that a note sheet and a copy of the Laplace transforms are permitted. Is that
so in this exam, the question was, what do you have available to you for exam number 1? You'll have 1 sheet of notes, and I'll give you this maybe in more detail, but I'll just tell you now on the next time we meet. But you'll have 1 sheet of notes, front and back, 8.5 by 11 inches. You can take the Laplace transform tables. I think that's table, I don't remember the number, but it's posted on D2L. You can bring a copy of that with you as well to the exam. Then a calculator, something to write with. If you want a ruler, if that helps you draw, if you want a protractor, if you're measuring angles, that's allowed as well. You may not need all of your drafting instruments, but you can bring what you need. You could even bring dividers, I guess, to measure distances and put those into a ruler. Anyway, that's exam number 1. Lab number 1, in terms of a write-up, the minimum that you need for submitting into the Dropbox, you need 1 team report per team. Not all 3 or 4 team members need to submit a report. Just 1 report is needed per team. Just make it clear who's on your team in terms of the submission. It should be written somewhere, printed legibly, hopefully. But the minimum that you need to put into the Dropbox is that exercise sheet for lab number 1. That's the bare minimum. I think it would be helpful for you in future to maybe actually generate a MATLAB plot of your step response and maybe indicate some of the points on that plot that you've now used on that exercise sheet. The intent is for you to actually be able to take the packet of material, that might be 1 or 2 pages, counting the exercise sheet, and refer to that and be able to talk your way through lab number 1, let's say at the end of the semester or prior to the final exam. You need to be able to look at what it is that you're submitting and be able to explain or walk yourself through that lab. You don't have to include all the process steps, all that detailed information, but you might want to, and in subsequent labs you will be turning in a little bit more maybe than 1 page. But a plot of your step response with peak time, settling time indicated on that response, I think would be beneficial to you. And it would be helpful for me if you put a number down on your page and I go, I wonder where that number came from. The other thing, I did look at a couple of submissions. Please be sure that when it says nominal system mass, that includes the mass of the carriage as well as the plates themselves. So if you need to correct your submission, I will look at the most recently uploaded submission, but I think if you are responsible for 3 masses, each of those are a half a kilogram. So that's 1.5 kilograms, but the mass itself is a half a kilogram. So your nominal system mass is actually 4 halves or 2 kilograms. And that influences the numbers that you derive as you go through that exercise sheet. Make sure you include the mass of the carriage, which is essentially another plate. So if you have 1 mass, you now have its half plus the half from the carriage, or you now have 1 kilogram for your nominal system mass. Is it clear what I'm expecting out of lab number 1? And hopefully you can look at the notes and watch the video for that to go in, execute the lab without too much difficulty. Today what we want to talk about really is related to lab number 1. How do you take a time response plot or picture and convert that into a transfer function? Or if I give you a transfer function, can you sketch the key pieces or parts of the response that might be associated with that transfer function? And we are going to concentrate on underdamped systems. So you have overdamped, critically damped, and underdamped. Underdamped means that we have an imaginary component to our 2 poles. That's what we mean by underdamped. If it was critically damped, we would have 2 real equal poles. If it's overdamped, you have 2 unequal real poles. But the underdamped case, as soon as you see that, you're thinking, oh, complex poles, meaning you have an imaginary component to those poles in your system. So here is our generic system. It's open loop. We're simply injecting or applying an input. Here I'm indicating that as a frequency domain concept, or the Laplace transform of the input, U of S, that passes through the system or is applied to the system or kicks the system, and it ends up giving you an output, capital Y of S. Let's now look at some examples. Suppose, for example A, this is transfer function G sub A, that it now consists of omega sub d over S plus sigma squared, that quantity, S plus sigma quantity squared, plus omega sub d squared. With that transfer function, where are the poles of G of S in the S-plane, complex S-plane? Can you draw those on the complex S-plane? Or where do you put your X's? This is like pin the tail on the donkey. Now we're at a birthday party. You now are walking up to the board and putting the pole on the S-plane. Where do they belong? 1, how many tails do you, how many poles do you have? Two poles. Why do you say 2 poles? So now, how do you determine how many poles you have in a given transfer function. What are you looking at? Numerator, denominator, both, neither? What are you focusing on when I say poles? The denominator. And what are you looking at in the denominator? Hopefully you're looking at the power, the highest power of S, and that will tell you how many poles you have in that particular transfer function, or let's say a signal if it was Laplace transformed. Now you have two poles that you're expecting to plot in this S-plane. Now I factored it in a way that after today's lecture you will be able to just instantly write down the location of those poles. Hopefully. The poles are then the values of S that cause that denominator to vanish or to equal 0. If you were to plug in S equal to minus sigma plus j omega sub d, that would cause that denominator to vanish or to become equal to 0. What did I just say? I said it was a minus sigma, and that's the real part. And then it has an imaginary part, omega sub d. If you plugged in, and so this is now at S equal minus sigma plus j omega sub d. That's the location of that pole. And that will annihilate the denominator, or let it go to 0, or force it to 0. If I've now pinned that pole on the S-plane, and if you examine that denominator, you should be able to instantly plot the second pole. Why? Because that denominator polynomial has real coefficients. If it has real coefficients, then you know that your roots appear in complex conjugate pairs. If you have real coefficients, you have complex conjugate pairs that are responsible for producing real coefficients. If I put some squirrely denominator that had imaginary pieces in it, then all bets are off. But in this class, we have real systems, R's and C's and L's. Those are M's and K's and B's. Those produce real coefficients in the denominator, and consequently we have complex conjugate pole pairs. That being said, then if you put in another pole, I'm sure I'm not going to get this, so I'm going to count. Try to make it a little bit close to reality. This is now a pole at S equal minus sigma minus j omega sub d, and that one also will cause that denominator to vanish. That's where we would at the party pin our poles. When I say underdamped, you immediately know that you're working off the real line. And now you have two poles that are somewhere, and we will learn a little bit more as we go through why those might be where they're located also. So now let's say that we have this system, G sub A of S, that's our system, and we apply initial conditions to it. So if this was an RLC circuit, we would apply maybe an initial inductor current, an initial capacitor voltage. Or if it's a mass spring damper system, we now initialize the velocity and position, and then we release it and see what happens. In our electrical circuit, we energize those energy storage elements, and then we just take our hands off and we watch the scope and see what happens with the inductor current and the capacitor voltage. Now, you can also produce the same type of response by hitting this system with an impulse. I like to kind of think about an impulse response. You go, well, that's an infinite magnitude. Well, really what the impulse response is doing is it's energizing instantly your energy storage elements in your system. And then what's it do? That impulse only happens at 0, and then it's gone. So it's now energized your system, and you're now watching what happens after you've energized these energy storage elements. So essentially, it's like an initial condition response. That's why I'm saying underneath this initial condition response, or an impulse response. You hit that system with an impulse and watch it perform. If the input is an impulse, what's the Laplace transform of that signal? What's capital U of S? What's the Laplace transform of an impulse? Now pull out your Laplace transform table and look at the pair, right? If you don't remember. That's why you have that. That's kind of your security blanket on the exam. You can now, oh, I'm not going to sweat that one. I know I have that information on my Laplace transform table. But this one actually, you could actually derive pretty quickly from the Laplace transform definition, I believe. What's the Laplace transform of an impulse? That's just 1, isn't it? So now, when we want to know what does the time domain waveform look like, y sub a of t, we are now inverse Laplace transforming capital Y sub a of s, which in the transform domain is equivalent to multiplying the system's transfer function with the Laplace transform of the input. That's our output. So we're now applying g sub a of s, or multiplying g sub a of s by u of s, and this impulse response makes that nice because now we really haven't changed the transform expression from the g sub a of s. We're just hitting it with a 1. Now we can go back and we can say, oh, what's the inverse Laplace transform of g sub a of s? That will give me y sub a of t. What's the inverse Laplace transform of that expression? Does anyone remember? If you inverse Laplace transformed that expression, what would you be expecting? So somebody pulled out their table and responded, which is fine. You'll want to be able to do that on the exam, definitely, if you don't know it, right? So they said, oh, that's in the time domain, e to the minus sigma t. That's the damping part. That's due to the real part of those poles. And then this structure, because I don't have an s in the numerator, I simply have something that's actually the damped frequency of oscillation in the numerator. That says, oh, I have a sine. So I have a decay, an exponential decay, together with a sine. I have e to the minus sigma t. Let me write that down so that we, and I don't know what that is. That's a placeholder. So y sub a of t is now e to the minus sigma t sine omega sub dt for t greater than or equal to 0. And now you could ask some other questions. Is this system stable? Or is this response stable? This initial condition response. What's going to happen as time gets big? Or you might even start thinking about sketching this. If you were drawing this, you might say, oh, I know that I have an exponential decay of e to the minus sigma t. So whatever that is, you actually have some decay, an envelope of decay that's determined by this e to the minus sigma t factor in your expression. And I hope we now all know how to draw or sketch sine omega sub d of t. What's sine of 0? 0. So we're starting here, and now we just, if we didn't exponentially decay, wow, your sine wave will look better than my sine wave, but you get a sine wave. Now you multiply those together. Maybe I shouldn't have damped that first one. But let me see if I have. So here's the pole 0 plot, and then here is what's really happening in MATLAB, if you can see that. Can you see that? Do you have young enough eyes? The actual response is the blue response, which is the product of this exponential decay and this sine wave. And the result then is the blue curve, which now says, oh, I'm having some oscillation due to the sine, but it's decaying because of this e to the minus sigma t influence or scaling. And this is what you could obtain if you simply said, oh, what's the impulse of g of a, where g of a you've put into MATLAB to equal the transform expression for that system. And so here is an illustration of that. You have a pure sine wave. That's the orange, yellow. I tried to do yellow but in the writing, but it wasn't even bright or dark enough to see, so I switched to an orange color. G sub a exponential is the exponential decay, and the blue is their product. And what happens? Well, the response, because it's an e to the minus sigma t sine omega sub dt, it's actually starting at 0, and then it starts bumping up, and then it decays. This is stable because we have poles in the left half plane. That gives us this minus sigma piece, which is e to the minus sigma t. That's going to decay exponentially with time. So this, if I was capable of drawing, I should have drawn that cosine differently to begin with. I apologize. And the blue curve now is going to try to follow that sinusoid as far as where it's crossing a magnitude of 0, but it's going to collapse or be squished according to the exponential decay. And that's now your response. What about this particular transfer function, b? What does the pole 0 plot of g sub b of s look like? Did everyone hear that? The denominator hasn't changed at all, has it? It should have exactly the same pole 0 structure that we had in G sub A. So depending on what sigma and omega sub d are equal to, we're now in the left half plane. Is our system, due to G sub b, stable or unstable? You have all of your poles in the left half plane. It's stable. They all contribute these e to the minus sigma t terms to them. Is that all we need to plot in a pole 0 diagram for G sub b of s? Now we actually have a 0, don't we? And where is that 0 located? at a value of s that causes the numerator to vanish, and that's actually at minus sigma. We now have a 0 right there at minus sigma. Questions on that? If that's the case, what's the initial condition response for that system? We already know that if it's an impulse, the Laplace transform of an impulse is 1. Now we want to know what happens when I inverse Laplace transform g sub b of s. What results? And now if you didn't know and you had your table of transforms, you would pull that out, wouldn't you? But what do you know the denominator is giving you? Those two poles tell you something about your behavior. They say your response is shaking. And they also say it's exponentially decaying. That 0 factor is actually telling you now instead of a sine, we have a cosine. And because it's exactly equal in terms of location in the complex S-plane as the poles, then it's actually a pure cosine. Now we have an exponentially damped cosine waveform that results from g sub p of s. Now we have a y sub b of t is now an e to the minus sigma t cosine omega sub dt for t greater than or equal to 0. And now you have a strategy for sketching that. You know you have an exponential decay, and you have a cosine. And now the cosine starts at 1 and just oscillates. How do you determine omega sub d from this picture? Or how do you determine e to the minus sigma t from this picture? Do you have a strategy for doing that? Because that would then, if somebody gave you this curve, this response, this blue plot, and they said, oh, what's the transfer function that realizes or is associated with that time domain behavior? Could you now find the exponential decay or this omega sub d? What is omega sub d? The imaginary component of the poles. Yes, it's also called the damped frequency of oscillation. So that is actually what's inside the argument of our cosine. That's our damped oscillation frequency. And in the picture, we could find that by looking at two consecutive maximums or two consecutive identical locations on that sinusoidal varying waveform. Meaning if I said, oh, here's a max right there, so I'll measure from there, and here's another max, and I go between those, that's now this period of oscillation, T sub d. And we know that omega sub d is 2 pi f sub d, but that's also f sub d and t sub d are reciprocally related, so this is now 2 pi over t sub d. If you can now go in and measure on your plot that distance in time between maximums or between minimums or any two identical spots, it's easier probably to pick maximums or minimums, you can now measure t sub d. Once you have t sub d, you just need to divide that into 2 pi, and you have omega sub d. Now you have the argument, or part of the argument, you have the omega sub d in your cosine expression. The exponential decay, if you could draw that envelope, now you know that you're starting, let's say, here, and what do you know about that decay relative to maybe a time constant? Could you find one time constant on that away in time from that exponential curve? If your expression now is e to the minus sigma t, or you might see that written as e to the minus t over tau relative to a time constant, sigma and tau are reciprocally related, obviously, now that you see that. What happens one time constant into the future? If we evaluate that when t, little t, is equal to tau, do we see that we get a scaling of e to the minus 1? So wherever we started up here at a value, let's say that was now x, you would be multiplying that by e to the minus 1 and finding that over here. And this point is now e to the minus 1 times x. And now you know that tau distance. You now know where, and that's not drawn very accurately, because what's e to the minus 1? Does anybody remember? You guys have all of these constants memorized. Yes, no. E to the minus 5 was less than 1%, 0.006 something, right? E to the minus 4, 0.018 or something, right? E to the minus 1, that's about 37% is what I remember, 0.367 or something. So now if you looked at that exponential, 37% of the height of x, now you know what tau is. Now you have a lot of information relative to this y sub b of t extracted from this time response plot. You've now identified omega sub d and sigma from that initial condition response. What if now we look at c? And we're after now, for this transfer function, g sub c of s, its pole zero diagram. And you can immediately, I hope, write down what we've already done in the previous two. Now you know where the poles are located. And what do you know about this response in terms of a time? Can you feel, can you see, can you think what this is going to be doing as a time response behavior? The poles tell you that information. They give you the exponential damping and the oscillation. These are underdamped. So now you know it's shaking, and you know that shaking is exponentially decaying with time, and it's all because you now have poles at minus sigma plus and minus j omega sub d. What else do we have? Do you know where the 0 is located? We can find the 0 by solving for the value of s that causes the numerator to vanish. We set that numerator equal to 0, and that will determine our zeros. In this case, it's going to obviously depend on the a's and the b's. So whatever that is, that's now where our 0 is located. We have a real 0. Now what do we have? And if I ask you on the exam, what do we have when we inverse Laplace transform g sub c of s? What would you do? What do you have? Now you have a 0 that's not where it was before in the previous example. In the first example, we didn't have a 0. Great. Now we have one that's not either of those two cases. What do? We do a partial fraction, or we start to look at what that system might, or that expression might be in terms of parts of an exponentially damped sine and an exponentially damped cosine. It's got to be a linear combination of those two. Let's now look at the numerator under that thinking. So we now have as plus b. Well, that is some alpha fraction of our cosine, exponentially damped cosine, and some, let's say, beta fraction of our exponentially damped sine. We can make that right-hand side look like the left-hand side by the appropriate choice of alpha 1 and beta 1. And that will now tell us how much of the cosine we have and how much of the sine we have. So we have those two making up or contributing to this new 0 location, as plus b. And we can do that, or find that. We now have alpha 1s plus alpha 1 sigma plus beta 1 omega sub d. We can find or solve for alphas and betas by comparing coefficients. If we look at the S1 coefficients, on the left-hand side we have a, and on the right-hand side, what's the coefficient of our S terms? We just have 1, and it's alpha 1. So now we know how much of the exponentially damped cosine we have. We have alpha 1, or a of that. What about how much do we have relative to the sine, exponentially damped sine? Now we have b on the left, but that's now equal to alpha 1 sigma plus beta 1 omega sub d. And we can now solve that for beta 1. And beta 1 now is b minus, we've already solved for alpha 1. And that's now going to give us the amount of exponentially damped sine that we have, beta 1 of that. We now can write down what y of s looks like. I'm sorry, y sub c. It's now going to be some alpha 1 e to the minus sigma t cosine omega sub dt plus a beta 1 e to the minus sigma t sine omega sub dt. And maybe that's not very easy to picture in your mind, but what happens when you have a sine and cosine at the same frequency? What can you do? You can combine those. Now we have a cosine with an offset or a sine with an offset relative to t equal to 0. So we could equivalently write this. We could say or y sub c of t is equal to some, let's say, a1 e to the minus sigma t cosine omega sub dt plus b1. That's how that sine and cosine combine. It's just a shifting in time of the cosine, or we could write it as a time-shifted exponentially damped sine. What has stayed the same in those three different expressions? Omega sub d, the frequency of oscillation, and the exponential decay. And those came where? From what? Where do you find those in this discussion? Sigma and omega sub d. Those were in our denominator, were they not? So let's now step it up a notch. The last three examples, we hit those systems with an impulse. That was like energizing the energy storage elements and then watching them decay. Let's now apply a constant input to this first system, G sub A of S, that we had. Let's now hit it with a constant amplitude, which is what you're doing in the lab. You're now applying a constant reference input of, let's say, 2,000 counts to make that mass try to move, hopefully somewhat close to 2,000. Depending on your system, it may not be quite there, may be more than 2,000. But what happens now when we try to do the step response of that very first transfer function that we started with? What's the Laplace transform of a step? And here I'm not saying a unit step, I'm saying just a constant, so my constant amplitude is A over S. If it was a unit step, A would be 1. What's y sub d of S now? Do you remember what g of A was? Now we're just multiplying it by 1 over S. This is now omega sub d A over S plus sigma quantity squared plus omega sub d squared S. Or maybe I put the S here if that makes you feel better. What's the pole zero plot of this look like? Is that what we have? That's what we had with G sub A. Poles at minus sigma plus and minus j omega sub d. And now we have another pole at the origin. Now when we inverse Laplace transform capital Y sub d of S, we have a little different set of transform information to deal with. What is the structure of that? So this is now the step response. Of our original, or our first example, G sub A of S. What is the structure? of the time response. How do you find structure? If you've had me for an earlier class, I kind of talk about structure of a response, and that means just what's the making up, how do you parameterize a time response behavior for this system? What pieces or parts are there? You don't have to give me the exact expression, but what are the formulas? Or what is part of that transform expression? So now we have the step response will be the inverse Laplace transform of this capital Y sub d of s. Yes? And how do you find the inverse Laplace transform of a transform expression? Partial fraction expansion. And what's that going to consist of? You now have something over s, you have a constant piece, and you have this sum of exponentially damped sine and cosine, which if we simply wrote it down structurally, we could say, oh, y sub d of t is going to be some a sub d plus b sub d e to the minus sigma t. That's coming to us from the exponential decay of our pole locations, our complex poles. Let's do the sine omega sub dt. We know the damped oscillation frequency is omega sub d plus c sub d t greater than or equal to 0. That's now the structure of our step response. A shifted exponentially damped sine added to a constant. And what does that look like as a function of time? If you've done your lab, you know what that might look like. Or if you've watched the video or looked at the notes. Isn't that just something that goes and shakes a little bit and then settles out? And where's it going to eventually end up? It's going to have some final value. We might call that, and what does this equal relative to this expression? As we let time evolve, time gets really big, what's y sub d of t going to become equal to? A sub d. There's our final value. So this must be a sub d. We're also going to learn how to use this time to peak to help us actually, and you've done this in the lab, that can also be associated with the damped frequency of oscillation. How quickly do you peak? That's sort of how much shaking you're moving. You could also use this distance. If your system is nice enough and has a couple of bumps, you may, because of the physical environment, you may not be kicking that system that hard, and it may only experience one bump, positive bump, before it quits. Now you maybe have some friction that we're not modeling coming into play in the lab. And so we may only have that one peak. Maybe we can't compare two maximums to give us this damped frequency of oscillation. We are also, where actually, let me just say that omega sub d, well, we've done that, right? 2 pi f sub d is 2 pi over t sub d, and we will find that it's also pi over, time to peak is pi over omega sub d. But we will also start looking at using this, let's say, y max. And what does that tell us about the system's behavior? That will actually give us the percent overshoot. We can compare that y max with the a sub d, figure out how much we actually bumped up, and that's going to give us a relationship between the real component and the imaginary component of our poles. All of these we will put together the next time we meet and be able to use this expression for y sub d and pull out or extract the transfer function of our system. We'll pick up at that point, or you can pick up at that point doing lab number 1 and complete this material.